Okay, welcome then guys to my first video on YouTube. I certainly don't think I'm going to become a YouTube internet sensation as I can't get this set up properly. I've been trying out loads of test videos. If anyone knows how to make videos, that'd be great because the resolution comes out really poor. So I'm hoping with the thick pen you're going to be able to see things, and it's going to in the end be quicker for me to upload videos onto YouTube and not have to worry about doing them on the portal at school, because it was caused me quite a lot of headaches. Excuse me, not a corona cough, I promise. Right, so you should though have looked at the videos on chain rule and starting to differentiate new products, new functions, like sin x, cos x, etx and ln x. And we're going to be using those today when we look at what's known as the product rule. Product obviously meaning multiplication, and we're going to look at how to differentiate the product of two functions. So in my first example, you can see we've got the function x squared, and then it's being multiplied by this other function 3x plus 1 all squared. This rule at the top, write this down, and as with all my videos now, start working with me. Pause the video whenever you want. You can try and preempt perhaps what I'm going to write. If we call one function u and one function v, then to differentiate y with respect to x, that's what I want to do here, then this is the formula that I use. The thing that was called u, I multiply it by the derivative of the v function, and the v function gets multiplied by the derivative of the u function, and the two things are added together. It will all start making sense when we set this out in quite a nice way. So let's just crack on. U is going to be x squared, and v is going to be 3x plus 1 all squared. We're then going to differentiate both of these separately. So differentiate x squared, obviously it's going to be 2x, and then differentiate 3x plus 1 all squared. You're going to start having to use chain rule, and I'm hoping you're getting good at your chain rule, and you're going to have to, maybe if you want to just go on another page, set that out in the chain rule way that we've been doing, but you'll get into the habit of knowing these answers quite quickly, because you're going to differentiate the bit in the bracket, which would be 3, and then times the derivative of t squared. So we're going to get 6 lots of 3x plus 1. Hopefully you can see this all right. I've left it too late in the day, so it's getting a bit dark, so apologies for the shadows. I'll try and do it earlier in the day. Been far too much DIY going on today. So we wanted to differentiate y with respect to x, so we're going to start timesing u with dv dx. Times those two things together, actually we've got an x squared times by 6 lots of that bracket. Neatest way, write the 6 first, then the x squared, and then the 3x plus 1. I like to have integers first. I'm then going to multiply the v with the 2x, and again it might be neat to just actually put the 2x in front, so we add that product on, and I get 3x plus 1 squared, and job done. We have differentiated it. What I would like you though to do at all times, really, you should always try and have a go at simplifying. If I just asked you to differentiate it, you could stop there. But we're going to simplify the answer as well. And there's some good reasons for doing this, and I'll mention those in a moment. So let's look for common factors. We've got two terms separated by that big plus in the middle. We've got a 6 and a 2, so common factor of 2. X squared and x, common factor of x. And then we've got a 3x plus 1 bracket and a 3x plus 1 bracket. So actually that bracket in itself is an entire factor and is common to both of those two terms. So then we've got some single bracket factorising. I'll probably use some square brackets at this stage just to separate them out from the other ones. What do I times that by to get here? So I need a 3, I need another x, but we only had one bracket anyway, so that's done. Second term then, the 2, the x is done. We've taken out one of those brackets, so there's just one of those brackets left, and then that's the factorising done. Within the squared brackets, I might just want to tidy that up. In fact, I can probably just do that. That little internal bracket isn't needed, so I've got a 6x plus 1 bracket. So if I factorise all of it, I would get that as my answer for dy by dx. And try and keep the notation there the whole time, really quite important. So let's have a look at a few more examples. Obviously you can pause the video. Okay, So our second one, we've got x squared sine 3x, so we just set up in the same way. X cubed, sorry, it's been multiplied with the sine of 3x. So 3x, remember, isn't a product, it's part of the sine function, sine of something. We're going to differentiate both of these, and at this stage, perhaps let's start pausing the video and you can get du dx and dv dx. I'm using quite a lot of chain rule within some of these questions, so I'm going to have to differentiate the bracket, which is going to be 3, and times it by the derivative sine of the bracket, which will give me cos of the bracket. And you'll start hearing some of the language that I sort of use to do chain rule sort of more quickly. So once you've got your 4 bits, hopefully you've written down the formulas on my previous page. I'm not going to keep flicking back. I've got times the u with dv dx. Again, I think I'd like to put the 3 first, then I'll write the x cubed, and then I'll write the cos. And then we add that together with v times du dx. I think the 3x squared first is neatest, and then we've got the sine bit. And that's it done. And again, if all I was asking you to do was to differentiate, you technically could just stop there. But I want you to get always thinking about simplifying, especially here when we've got common factors. So common factor of 3, x squared is common to both. We've got cos of 3x and sine of 3x, so there's no common factors there. Remember, the 3x is a part of the sine and cos functions there. So let's look at what I need to times that by to get here. So I'm missing an x and the trig part. And then I've taken out the 3, taken out the x squared, so I've just got the sine part left. There isn't anything within my squared brackets to sort out, so I could just stop and leave it there. Whether I want to write it with a curly bracket, that's entirely sort of up to you. Okay, example number 3. We've got 4x plus 1 all multiplied by e to the 2x. So start writing out what u is, what is v. So it's important at the moment, it's obvious you know you're doing product rule, but when you're on your own doing this later on, or in months to come, is spotting that we're timesing 2 separate sort of functions together. Differentiation 4x plus 1 is nice and straightforward. Seems to be the second one I've always used a little bit of chain rule. That's not a hard and fast rule, it's just what's happened. The bracket is the 2x, I'm going to have to differentiate that. And when I differentiate e to the power of something, I get e to the power of something. So my dy by dx, do you know the formula already? When it's set up like this, I don't think you need to look back at the formula. We're going to times those 2 things together. And then we're going to times those 2 things together and add them together. So when I times these together, I'm going to put the integer first. I could put e to the 2x and then that afterwards, but I always get worried that you might write something that looks like the power. So I'm going to put the 4x plus 1 first, and because it was multiple terms, it needs to have a bracket around it. Then I've got e to the 2x. Then add on, times those 2 things together, that's nice and straightforward, not much there to do. Again, nice and sorted. Let's just have a get simplifying. We've got a common factor of 2's, and we've got the common factor of the e to the 2x's. What do I times that by? Well, just purely the 4x plus 1 there. And then this term, we've taken out the 2, so we need to keep a 2 in there. So within my squared brackets, this is a bit of tidying up. We've just got the 1 4x plus 1 bracket, but you can add that 1 to that 2. And this is why I don't really sort of like that. I can leave it like that, there's no problem, but just if your hand was getting a bit dodgy, that goes up the page a little bit, does it get confused with the power? So I could potentially write the answer like that. And these were all dy by dx's. Carrying on from there, so that was okay. Fourth one for you to do. Start writing down u and v. We can get quick at this. It's more the time it just takes me to write it on the video. So I'll try and be quick for you, just so the video is not too long. Again, I'm going to have to do a bit of chain rule here, differentiate the bracket, I'm going to get a 2. When you differentiate ln of something, you get 1 over the something, 1 over the bracket. So we're going to, it'll be 2 times 1 over 2x. So doing a little bit more working out here for you. But if I do 2 times 1 over 2x, it'll be 2 over 2x. That'll just be 1 over x. So that simplifies down quite nicely. Again, look back at the differentiation chain rule videos on the portal. I might redo those videos for YouTube, see how we get on. So what am I timesing together? The u with the dv by dx. As that's a fraction, I'm going to just times that with the top. So 1 lot of 5x minus 3 over x. And then I'm going to times those two things together. So that'll be 5 ln of 2x. There aren't any common factors here and here, so I can't really do much. And I know someone asked me the other day about can I move the 5, so it was a power of the 2x. You could do, in this case I don't think it's going to give you any value, it's not going to make much sort of difference for what you're wanting to do. So there's some examples of differentiating chain rule. Just before we move on, I'm going to just show you a few questions. You might have saw a glimpse of them just now. I just wanted to think about why I've factorised some of these answers. Just a sketch of a random curve here. Don't know really what it is, what its function, but what I'm interested in a lot of the time is stationary points. And stationary points are, I can see 4 of them, perhaps maybe 5 there on there. And of course, what are stationary points? They're when the gradient function is equal to 0. And I haven't asked you to do that in the chain rule videos, but I certainly should do, and we'll start asking you tangent and normal questions. But there's a reason why I was doing the simplifying the answers, where these are getting more sort of complicated. Just imagine if I'd asked you to find stationary points on this function here. In fact, it's a quartic. That might help us to think about how many stationary points it potentially could have. And certainly if I wanted to sketch it. So here's my differentiation. I factorised it, and let's just say I'm going to carry on and make it equal to 0. Well, as it's factorised, one big term, this solving is going to be straightforward because I've got these 3 factors to look at. So x will equal 0, x will equal minus 1 over 3, and x will equal minus 1/6. Nice and quick. If I'd asked you to put equal 0 at the end there, I don't think you'd have been quite so keen and wouldn't be able to spot those answers straight away. So you can do here. Don't forget, if you're asked to do stationary points, you might be asked to find the coordinates. So I need to find the y coordinate. So each of those 3 individual values, I need to sub back into that to work out their y coordinates. I second differentiate if I'm going to start doing the nature of the stationary points, and if I'm going to differentiate this again or even this, that's getting quite a lot of work, so perhaps I might not want to do that. We won't ask you to do totally ridiculous things. Looking at this one, the factorising, again, if I wanted to find stationary points, make it equal to 0. We've got a common factor, 3x squared, so we're going to have x equals 0. And then that big squared bracket is going to equal 0. And that one, because it's not a nice linear function, isn't so good, and I'm just not so sure on that one at the minute. There's quite an amount of work to do, so we're not going to worry about solving that one. But ones with exponentials, I certainly do like thinking about. So if I was finding stationary points here, we've got the constant, so there's no factor there to worry about, but we can make that bracket equal to 0, so we can have x is equal to minus 3 over 4. That was 4x plus 3 equals 0. That's what I'm doing, isn't it? And of course I've solved it into that. What about e to the 2x equal to 0? Have a think, pause the video for a second. What's the answer going to be? And of course the answer is it cannot equal 0. Let's just have a little think about an e to the x graph, or any exponential graph. It's asymptotic towards the negative axes here, and doesn't cross, so it doesn't ever equal 0. This last one that I did, don't want to try and solve that, that's going to be horrible. So here we go, there's 5 questions for you to have a little go at. So pause the video, have a go at doing these. I will set you some more questions with solutions, and then there'll be a little assignment, but just immediately you want to have a look at some of these. So pause the video because I'm about to turn over and show you the answers now. That was me just being quiet. It's like pausing. Question number 1 and 2. I've not shown you the U and the V, but just quickly answer so you can just check. So keep pausing the video to see what you've got, but you'll see that I've simplified answers as well. It's good for you to try and do that. There's possibly that you might write these around the other way in the end. It doesn't matter too much. There's 3 and 4. And then finally, there's question number 5. So that's the product rule. Fair bit of chain rule going on in there as well, so it's getting ever more sort of complicated. Apologies for the big shadow. That's the shadow of my phone. So I'll try and do these when it's a bit sunnier. But there we go. See you soon. Bye.